Okay, so on my last video, I got cut off time-wise, ran out of storage on my computer. So we're going to start back where we left off with binomial. I'm going to finish up the binomial notes, and then we'll go into geometric in this video. Okay, so we learned in the first part of this video about binomial distributions. We talked about how to use the binomial formula, which is on your formula sheet. We talked about how you could use binomial PDF if I wanted the probability of exactly a certain number of successes. And we used that formula and the calculator key to come up with all of the individual probabilities in a probability distribution, all of these. And then we were just talking about how we could find those probabilities from this probability distribution, or we could use binomial PDF if I was looking for an exact probability, like we did for each one of these, or CDF if I wanted cumulative from a certain point back. And so what we just did in the last video at the end was I wanted the probability of less than 3. Well, less than 3 is not including 3, but everything less than. And so what the CDF key does is whatever number you put here, that's the highest number it wants to include. And it's going to take that probability and everyone below it and add it all together. So we go to second vars. We go down to binomial CDF, N, P is 0.58, K is 2. Notice how binomial PDF gave us the exact probability at 2, 0.157, while CDF gave us everything up to that point. So it was 0.005, 0.045, and 0.157 all added together, and that's what we got when we used that table. Now, make sure that whatever number you put here when you use CDF, that's the highest number you want to include. So it's very important. If it's not including 3, the highest number I want to include is 2. Now on this next one, I could still use binomial CDF. And this time, the highest number I want to include is 3, because it's including the 3. So again, just to practice this again, second vars down to binomial CDF. 6, comma, probability of success is 0.58, comma, this time we're going all the way up to 3, and that's pretty close to what we got by hand. Now, I have a calculator key that finds exact probabilities. That's PDF. That's how we found all these individual probabilities of exactly this many successes. I have a calculator key that goes from a certain point back, cumulative. That's what we did here and here, from 2 back or from 3 back. But what happens if I want above? Well, if I want above a certain number, I don't have a calculator key that does that. But what I'm going to have to do is realize, something we talked about in the last chapter, that all of these probabilities should add up to 1. So if I could find what I don't want, then I could subtract it from 1 and it would give me what I do. What I would recommend, especially when I'm looking at above a number, I would write out all of the possibilities. So I could have exactly 0 successes, exactly 1, exactly 2, exactly 3, 4, 5, or 6. If I'm looking for greater than 3, where is greater than 3? Well, greater than 3 would be 4, 5, and 6 added together, wouldn't it? So what don't I want? Well, I don't want from 3 back. And so what I can do here is I can say 1 minus binomial CDF, and I can subtract away this cumulative, all of these together, probability. So 1 minus, N is still 6. Probability of success is still 0.58. But what I don't want is 3 and back. So when it's below a certain point, the number I put here is the highest number I want to include. When it's above, draw your number line, circle what you're looking for, and you're subtracting away the highest number you do not want to include. Okay? So I can do the whole operation as 1 on my calculator. I can say 1 minus, second vars, go down to binomial CDF, total number 6, probability of success is 0.58, and I'm subtracting away 3 and below. Is that pretty close to what we found when we did it by hand? Sure is. So when you're doing binomial, make sure, first of all, that it is out of a fixed number of observations, that you're looking for a certain number of successes out of that fixed number, that you have a situation where it's either a success or a failure, all your observations are independent, and the probability of success is the same. You have this formula that you can use, and you can do this by hand, and we practiced doing that by hand earlier. Okay, how to plug in and how to use that NCR button on the calculator to do this portion. You can use your binomial PDF for each particular probability, and you can use CDF for cumulative. If it's from a certain point back, then I just use CDF and include the highest number I want to include. If it's from a certain point up, then you're going to subtract away the cumulative of what you don't want. Okay? Now, geometric is going to work very similar to binomial. In fact, you'll notice when we look at geometric that some of the rules are the same. Okay, for geometric, it's still a situation where it's success or failure. All the observations are independent of one another. The probability of success is still the same for each observation. But what's different is, in geometric, I do not have a fixed number of trials. Instead, I have an infinite number. I am going to see how long it takes until I get a success. Okay? Here are some formulas. So if I want to find the probability of it taking exactly K trials to get to a success, so notice that instead of the number of successes, it's how many trials until that success happens. So if I'm looking at the success happening on the Kth try, then it's the probability of failure raised to how many failures we had before the success happened. Remember, 1 minus P will be the probability of failure. We have a calculator key that'll find that probability, and it's geometric PDF. Now notice there is no n in my input. That's because there is no n. There is no fixed number. All I have is the probability of success, and then whatever trial I want that success to happen on. I have a geometric CDF key. This works very similar to the binomial CDF. It's cumulative. It's what's the probability of getting a success in the first however many trials. If I want the expected number of trials before I get a success, or the mean, remember mean and expected value are the same, right? So if I want the expected number of trials until a success happens, I'm just going to say 1 over the probability of success. Now, unlike binomial, when I create my probability distribution model, since X is how many trials until the success, I can't have a 0 trial. So the earliest trial I can have is a 1. Also, unlike binomial, I don't have an ending. There is always a possibility it takes another trial until the success happens. And so I'm going to have an infinite distribution. And so because of that, all of these probabilities are going to approach the sum of 0. But there's always a possibility, while it gets very small as you get further out, but there's always a possibility it takes one more trial to get to that success. Okay? Some situations that would be geometric, like how many times do I have to roll a die to get a 6? Or how many times do I have to flip a coin to see heads show up? Or how many times do I have to toss a piece of paper towards the trash can to make it in? Anytime you're looking for how long until a success happens, that's going to be geometric. Okay, so let's try one. All right, Travis Jordan completes 56% of his passes. How many passes is he expected to make before a completion? Well, what is this asking for? Well, if it's expected, my expected value is the same thing as the mean, right? Now, is this a geometric distribution? Well, of course, because I'm doing it in the geometric notes, right? But we know it's geometric because success or failure, either he completes the pass or he doesn't. All the observations, each pass is going to be considered independent of one another. The probability of success, 0.56, is going to hold true for each throw. And our variable of interest is how long until the completion happens. So how long do we expect that to take? Well, I just do 1 divided by the probability of success to find that expected value. So 1 divided by 0.58 is 1.72. So I expect him to take between 1 and 2 passes before I see a completion happen. Now, what's the probability that he makes his first completion on the second pass? Okay, well, I can do that one of 2 ways. I'm going to come down here where I have a little more room. I can use my formula. On the notes page, let me put that up here so you can see it. It says that if I'm looking for exactly a certain number of trials, so I'm looking for it to happen on the second try, then I'm going to say 1 minus P, that's the probability of failure, right? So if 0.56 is the probability of success, then 0.44 is the probability of failure, raised to how many failures? So k minus 1. So that means that we had one failure, right? Times the probability of success, because it happened on the next one. Okay, so if we multiply that out, 0.44 times 0.58, that probability is 0.2552. If you had wanted to use your calculator, this is going to be geometric PDF. Again, there's no n, so it's just p and k, so probability of success is 0.58. I'm looking for it to happen on the second try. So geometric PDF and CDF are in the same place as the binomial. You go to second bars, but it's all the way at the bottom. So you gotta scroll a little further. Okay, so geometric PDF, and all I can input is just P and K. So just probability of success, and see, it's very close to what we did by hand. Okay. Now, on number 3, it says, what's the probability it takes more than 3 attempts before he completes a pass? Okay, more than 3 attempts. So that means that it takes 4 or more, right? Now, while it's continuous, all of them should add up to approximately 0, right? So what I can do is the same idea I did back with binomial. What I don't want is 3 and back, right? So I can say 1 minus 3, 2, or 1. And the easiest way to do that is to use our geometric CDF key, because that's cumulative, because that'll take what I don't want and back. So probability of success, and I'm looking for 3 or less. So we can say 1 minus, second bars, geometric CDF, 0.58, comma 3, and the probability that it takes more than 3 attempts is pretty generous, but 7%. Okay? All right, what I'd like to do now is I want to kind of review a little of both and do some different probabilities that are associated with both of these. And so one of the first things I want to do on each of these is decide, okay, are we dealing with binomial or are we dealing with geometric? Okay? So what's the main difference between the two? Well, the main difference is that in binomial, you have a fixed number of observations. Out of this many, I'm looking for this many successes. In geometric, there is not a fixed number. It's infinite. It's how long until a success happens. So that's the main difference between the two. All the other 3 are exactly the same that have to be in place, right? All right, so let's look at a situation and see if we can figure out, is it binomial, is it geometric, and then how can we handle it? So a manufacturing process produces, on average, 3% defective items. The company ships 12 items in each box and wishes to guarantee no more than 1 defective item per box. What's the probability that the box will fail to satisfy the guarantee? Okay, so I'm looking at a situation where we have a success or a failure. Either it's a defective item or it's not. I'm going to assume that all the boxes are independent of one another. Probability of success they gave me was having a defective item, 0.03. And look at this. I have a fixed number, don't I? That makes it binomial, doesn't it? Okay. Now, I could have, out of those 12 items, I could have 0 defective items. I could have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12 defective items, right? They want to guarantee no more than 1 defective item. So they want to guarantee that this is all that happens. Either 0 or 1, but no more. I want to know the probability that the box fails to satisfy that. I want to know the probability of having 2 or 3 or 4 or 5 all the way up to 12. So how can I do this? Well, I don't want these 2, right? Because I want to see what's the probability of them failing the guarantee, which will be having more than 1 defective item. So I'm going to say 1 minus binomial CDF, because I'm doing more than 1 calculation, right? Okay, remember in binomial we have n, p, and k. N is 12. Probability of success of finding a defective item is 0.03. And I'm subtracting away 1 or less, because if they had 1 or less, they satisfied the guarantee. So on my calculator, if we do 1 minus second bars binomial CDF, 12, comma, 0.03, comma, 1. The probability of this happening is about 5%. Okay, let's try another one. Suppose it's known that 80% of people exposed to the flu virus will contract the flu. Out of a family of 6 exposed to the virus, what's the probability that? Okay, let's first decide what we're dealing with here. Which one are we dealing with? Is it binomial or geometric? Well, right here, this tells me it's out of 6. I have a fixed number. This is binomial. Okay? So that means I can have 0 people will get the flu, or 1, or 2, or 3, or 4, or 5, or 6. So the first probability they say is, what's the probability that no one would contract the flu? So I'm looking for a particular probability. Well, I can use my formula. Okay, if I want the probability of exactly k successes, I do n choose k to figure out how many k successes I can arrange in observations. Probability of success raised to the number of successes. Probability of failure raised to the number of failures. Or I can use my binomial PDF key, right? So we're going to do both. Okay, so n is 6. I'm looking for 0 successes among 6 observations, right? Probability of success, well, what is a success here? A success would be contracting the flu. I told you, success is not always a good thing. All right, so probability of contracting the flu is 0.8. We don't want anybody to do that. Okay, probability of not contracting the flu then is 0.2, and that means that all 6 are doing that, right? Okay, 6, choose 0. Well, that's just going to be 1, because there's only one way I can have nobody get it, right? But just to practice that calculation, you type in 6, then you go pick up that NCR key. So you go to math, over to probability, there it is right there, and then 0. Okay, so that's just 1, times 0.8 to the 0, 1, times 0.2 to the 6th. Okay, so really small, isn't it? Unfortunately. So that's 0.1, 2, 3, 4. Okay, or you could write it 6.4 times 10 to the negative 5th, either way. Okay? Now, if we were doing on our calculator, second bars, binomial PDF, right? I'm doing PDF because it's a particular probability, exactly 0. So n is 6, p is 0.8, and I'm looking for exactly 0, and c gives me the same thing. Okay? What's the probability that all will contract the flu? Okay, so we're looking for the probability that all 6. So I could do the same thing again. 6 choose 6. This time it's 0.8 to the 6th, 0.2 to the 0. Okay, so 6 choose 6 is going to be 1. 0.2 to the 0 is going to be 1. So 0.8 to the 6th power is about 0.26-ish. And if you, again, did the same thing, binomial PDF, so second bars, binomial PDF, 6, comma, 0.8, comma, 6, and see it's the same thing again. All right, the probability that exactly 2 will get the flu. Exactly 2. So 6 choose 2. So probability of getting the flu is 8, and I'm looking for 2 of them getting the flu. Probability of not getting the flu is the opposite, 0.2, so that means the other 4 are that, right? Okay, so 6, math, probability, NCR, 2. So there are 15 different ways of arranging exactly 2 observations, 2 successes. 0.8 squared, 0.64, 0.2 to the 4th, and then we multiply all that together. There's your probability. Oops, didn't put an extra 0 there. 0.0153. Or we could have just said 0.015. Okay, and if you wanted to try that again, that's a PDF again, right? So second bars, binomial PDF, because it's a particular probability looking for exactly 2. So n is 6, probability of success is 0.8. We're looking for exactly 2, and it gives us the same thing as our formula. What about at least 2? Well, at least 2 would be 2 or more, right? If I want the probability of at least 2, Okay, well, I don't have a calculator key that goes up, right? So I know I'm going to be subtracting. So I'm going to need to subtract. I know I have 6. I know the probability of success is 8. What I don't want is from 1 back. So remember, we have this binomial CDF key that goes from a certain point back. If they had said less than 2, then I would have just used the CDF key. But if I want a greater than, I've got to say 1 minus what I don't want. So don't forget, binomial PDF finds a particular probability, exactly this many successes. CDF goes from a certain point back. And so whatever number you put here, it's including that in the calculation. So be careful about that, okay? So the highest number I want to subtract away was 1, right? Because we wanted at least 2. At our next meeting, so today you're going to practice with some book work. But at our next meeting, the next class, we'll actually have a practice worksheet that's going to help with this. Okay, so the probability of at least 2 is pretty high, isn't it? Okay, now when it says how many would you expect to get the flu, well, that's just the mean. And the mean in a binomial situation, it's on your formula sheet, is n times p, so 6 times 0.8, which is 4.8. So I expect about 4.8 of them to get that. If I want to find the standard deviation of this, then I've got to take the square root of n times p times 1 minus p. So that's going to be 6 times 0.8 times 0.2. And then I got to take the square root of that. And so that would be, say, about 0.98, my standard deviation. Okay? All right, let's look at this next one. The most common data collection method in consumer and market research is a telephone survey. A major problem with consumer telephone surveys, however, is non-response. How likely are consumers to be at home to take the call, and if at home, how likely are they to take part in a survey? To answer these and other questions, R.A. Karen and R.A. Peterson directed a study of over 250,000 random digit dialings, but both listed and unlisted telephone numbers across the United States. The probability of a completed interview was assessed to be 0.084. What's the probability that 5 calls must be made before the first completed interview is obtained? What are we looking at now? We're now looking at geometric, okay? And so for geometric, I'm looking for how long until this occurs. Here's the probability of success. Okay, it says what's the probability that 5 calls? Exactly 5. So I'm looking for the probability, our rules up here for geometric, that the success happened on the 5th call. So I need the probability of failure, 1 minus p. So 1 minus 0.084 is 0.916 times the probability of success. Oops, that's 4. Sorry. There were 4 failures until it happened on the 5th one. Okay. Or I could use geometric PDF. And remember, the only thing I can plug in here is just probability of success. And K, what I'm looking for. So I'm looking for it to happen on the 5th call. Okay, so if we do it by hand, 0.916 to the 4th times 0.084. If we use the calculator, second bars, go down to geometric PDF. Oops, too far. 0.084, comma 5, and it should be the same thing, and it is. So either way. All right, now the second one says, what's the probability that at least 5 calls must be made before the first completed interview is obtained? So at least 5 calls. At least 5 means 5 or more. Okay, so here's where I'm subtracting again. If they had said less than 5 calls, then I could have just used the CDF key, right? But since they want greater than, I know I've got to subtract it from 1. So I'm going to have to say 1 minus geometric CDF, probability of success. Okay, what I don't want is 4 and back, right? If I want at least 5. So on your calculator, you're going to say 1 minus, second bars, go down and find geometric CDF, 0.084, comma 4. And there's the probability. Okay. Now, we're not going to talk about standard deviation for right now. We might come back to that later. Right now, if it's geometric, the only thing we're going to talk about is the mean number or the expected number. So what's the expected number of calls before the first completed interview? Well, in geometric, we find that the mean is just 1 over the probability of success. And so we're going to say 1 divided by 0.084. And it looks like it's going to take a while. It's going to take at least 11 calls, maybe even almost up to 12. Okay, so the biggest thing when you're dealing with these problems in this unit, you first got to decide, am I dealing with binomial or am I dealing with geometric? Okay, so am I dealing with, is it out of a fixed number and I'm looking for the number of successes, or is it how long until the success happens? Once you've decided if it's binomial or geometric, then you've got to decide, okay, am I looking for a particular number of successes, exactly this many successes? That's going to be binomial PDF. Or if it's geometric, am I looking for the success happening on a specific trial? That's geometric PDF. Okay, or is it I'm looking for a group up to a certain point, then I'm going to use a CDF key. Or is it above a certain point? I need to use 1 minus the CDF key. Or am I looking for expected value? That's the mean. So again, first thing you got to do, am I dealing with binomial or geometric? Separate that out. Then am I looking for exactly a certain number? PDF. Am I looking for a cumulative up to a certain point? CDF. Or am I looking at above a certain point? That's 1 minus the CDF. Expected value or mean, we have the formula for both situations. Okay. Make sure you're practicing. Try those practice problems. Let me know if you have questions.